Okay, welcome to week 8 of the problem solving session for the NPTEL course Dynamical System and Control. Let's begin with revising the topics that have been covered in the last week. So, the last week typically concerns various transformations which allows us to transform system to Jordan form or companion form, and then designing state feedback controllers for achieving asymptotic stability or stability. So first of all, we got the concept of duality, which says that if we have system x dot equals to ax plus bu with measurement cx, let's call this system as 1, and if we have another system, let's say that it as x dot equals to minus a transpose x plus c transpose u with measurement b transpose x, and let's call this system as 2. Then what duality says? The duality theorem, it says that if, so we suppose that system 1 is observable. Now when we say system 1 is observable, we know that we can find the matrix M, that is the observable Gramian matrix. So it is nothing but, if phi is the state transition matrix, then we can write for system 1 with C as the output matrix. We can find the matrix M, and this should be non-singular. All right, and we say that system 2 will be controllable. Now for 2 to be controllable, then again we can find some matrix N where we can write the state transition matrix, and here we have the controllability matrix as C transpose, so it is C and then transpose of this one. All right, now since both these A and minus A transpose will have same state transition matrix, then this phi and this psi are equal or same, then that typically means that M and N are same matrices. So that gives us the concept of duality. So what it tells us that if system 1 or when system 1 will be observable, means the system of the form x dot equals to x plus bu with y equals to cx is observable if and only if this system 2 is controllable, and vice versa. That means if system 1 is controllable, then if system 1 is controllable, system 1 is controllable if and only if this system 2 is observable. So what I'm saying is that system 1 is observable if and only if it's dual. So its dual is system 2, if and only if system 2 is controllable. And similarly, we can say that system 1 is controllable if and only if system 2 is observable. So that's basically gives the concept of duality. All right. Then we also have this Jordan form where it says that so we are not going through the transformation on how can we form the Jordan form, but let's suppose that we have the Jordan form of the system J. So let's say that let there exist a transformation acting on the state matrix. So there exists a transformation P which acts on the system matrix A, which gives us the Jordan form of the system J. So let J be the Jordan canonical form. Canonical form of A, obviously. And if we have the transformation P, then the control matrix also we can write as P inverse B. It will also be transformed, and let's say that the transform matrix is D. Then the resulting system, so we have the original system as x dot equals to ax plus bu. So after having the Jordan canonical form, we say that the original system x dot equals to x plus bu is controllable if and only if the Jordan system, that is z dot equals to jz plus du, is controllable. All right. So suppose we are given the Jordan form of the system, and the question asks about whether the real actual system is controllable or not. Then we can check controllability of this Jordan system, and then that equally means that our actual system is controllable. All right. And how does this Jordan form looks like? So in Jordan form, we have the diagonal structure based on the eigenvalues of the state matrix A. So for example, let's say our matrix A has eigenvalues lambda 1, lambda 2, and lambda n, and all of them have multiplicity of 1. Then the Jordan matrix will be nothing but a diagonal matrix. But if we have any eigenvalue of multiplicity, let's suppose lambda 1 has multiplicity of 3, lambda 2 has multiplicity of 2, and also suppose that it has geometric multiplicity of 1, then for these two eigenvalues, the Jordan matrix will look like, so we have lambda 1, lambda 1, lambda 1, and lambda 2, lambda 2. Since we have geometric multiplicity of 1 only, so the Jordan form will be of 1, 1, 1, and then oh sorry, this will be lambda 1 and 0, 0, 0, 0, all will be 0. So this is how the Jordan matrix will look like, and this constitute the Jordan blocks. So this is the Jordan block, and this is the another Jordan block. All right. Now suppose if lambda 1 So this is the arithmetic multiplicity. Now suppose lambda 1 has geometric multiplicity of 2, then how the Jordan form will look like? It will look like, so the lambda 2 is having geometric multiplicity of 1, so it will look like this. And for lambda 1, since we have geometric multiplicity of 2, then the corresponding, so we will have two Jordan blocks corresponding to 1, because now we have geometric multiplicity of 2, so it will have two Jordan blocks. So one constitutes this Jordan block and another will be this lambda 1 only, and then another Jordan block because of lambda 2, and all will be 0. So this is how we can identify the Jordan blocks and also its geometric multiplicity based on the given Jordan matrix, Jordan form. All right. Then we discuss the companion form. So how can we transform the system to its companion form? Companion form, basically, for example, we have the state transition matrix A, we have the state matrix A for the system x dot equals to ax plus bu. Then this system can be converted to companion form if and only if the system is controllable. So if a question asks about converting the system to companion form, we must check whether the system is controllable or not. So for if we have checked the system is controllable, then only we can convert it to companion form. So we will suppose that the system is controllable, then the companion form for this system matrix A can be found by the characteristic equation of the state matrix A. And let's suppose we have the characteristic equation as uh, lambda n plus a1 lambda n minus 1 plus a2 lambda n minus 2 up to, let's call it an equals to 0. Then the companion form will look like so this comes here, minus an minus 1 up to minus a1. So these coefficients will appear in the last row of the companion form, and the first will be 1 0, and after that we will have a diagonal of 1, and then all other elements as 0. And the B matrix, so this is the transformed AC, and then we have BC as 0 0 up to nth element will be 1. So this is the companion form for the system x dot equals to x plus b. All right. So that's it. Now let's begin with solving problems. Okay, so let's take up our first question based on the observability. So, or controllability. You have to check the controllability of the following system. So system 1, system A is given as x dot equals to 1002 into x plus 1 1 u and second system is given as x dot equals to 1002 into x plus e to the power t and e to the power 2t into u. You have to check the controllability, whether the system is controllable or not for both system A and system B. Okay, let's solve this question. The system 1 is a simple linear time invariant system, but the second system is basically a linear system, but it is time varying because of this time varying matrix B. So for the first system, it is very easy. So we have to just check the controllability matrix BAB because the second order system. Now, if we solve this, we will see B is 1 and AB will give you 1, 2. Now, if we check the determinant of it, it is 2 minus 1 equals to 1. So, since determinant is non-zero, it has full rank, so this system is controllable. Now what can we say about the second system? Since as you can see the time varying matrix B of this system, you can see that these values are non-zero for all time because exponential function is never zero, and it has positive t as its uh, exponent. So one can infer that since this P matrix is never zero, so control is acting for all time, so the system must be controllable. But we cannot give guarantee without checking its controllability Gramian, okay? Because this matrix will not give us any information because this is explicitly, this condition is explicitly for linear time invariant system. Since this is a linear time varying system, we must go through calculating the controllability Gramian matrix. So for controllability Gramian matrix, which we call as WC, which is given as integration of the state transition matrix d tau. So we have to calculate this integrand in order to check whether the controllability Gramian is singular or non-singular. So when it is non-singular, we can say that the system is controllable. So let's check out this one. Now when we find out the state transition matrix, because this is all needed for the Gramian matrix. Now the state transition matrix, since the state matrix is diagonal, we can easily say that, we can easily find out that it is nothing but exponential of the uh, diagonal entries. All right. And then we have to find this product. So let's find out this product, which is t tau into b tau and it is also very easy to calculate. It is 0 0 and then e tau 2 tau. Now since we have this, when we multiply, we will get this multiplication as e to the power t and e to the power 2t. You can easily calculate this. So the controllability gradient can be given as wc t naught to t it is nothing but this matrix e to the power 2t and then the transpose of the same. So the transpose is e to the power t e to the power 2t and we have to integrate with d tau. So first calculate this matrix. It is e to the power 2t, e to the power 3t, 3t and 4t. Now when you see this matrix, you will see that we have no variable tau in this. So the integration will just give you the factor t minus t naught. So it is t minus t naught, t minus t naught so now let's calculate its determinant. Now this is our controllability gradient and this should be non-singular for the system to be controllable, but when you calculate its determinant, you will see that it comes out to be e to the power 60 and minus e to the power 60. That means that the determinant of WC is 0. That means system is uncontrollable. So what's the conclusion? The conclusion is that even though we have the same state matrix, and for the system 1 we have a constant B matrix with all entries with no entry as 0, but the same system, if we have the same state matrix, and in this case also we have no entry 0 in the B matrix because this exponential is never going to be 0, even we have this case, but the system is uncontrollable even though the earlier system was controllable. So we must be very careful while deriving conditions for time varying system, because that could give you a really strange picture. What you look is never what you expect it to behave. So we must be very careful while dealing with any non-linear system or time varying system. All right. Okay. So this is our question number 2. So we start with the system. So consider a linear time invariant system x dot equals to ax plus bu, and we say that this system is equivalent to the differential equation which we give as x double dot plus ax dot equals to bu. Okay, then the system is controllable if b is we have to fill. So we are given a linear system, and we say that this is equivalent to this differential equation, and now we are asked to find out condition on B such that the system is this system is controllable. This one is very quick to solve. Let's uh, convert this differential equation, which is x dot equals to bu. So let's consider x1 as the variable x and x2 as the variable x dot. Then what we can write? We can write the system as x1 dot is x2 and x2 dot will be minus a x2 and plus b. So this is the system given to us. So for this, the matrix A we can write as 0 1 and 0 minus a, and the matrix B we can write as 0 and b. Now we can easily check the controllability of this one. So we have to find the controllability matrix, which is P A B, which gives the form 0 B, and BAB will give us B minus AB. Okay, and we need this matrix to be of full rank, that is of rank 2. So its determinant should be non-zero. So its determinant, when you calculate, it is minus b square. Okay, now for system to be controllable, its determinant should not be 0. The condition for controllability is b not equal to 0, because when b equals to 0, determinant will be 0 and will be of reduced rank. Okay, let's move to question number 3. Suppose we have system given as x plus bu, where A is the matrix 1 1 1 0 and B is the matrix 1 0, with x0 is equal to x naught, and let we have the companion form for this system given as y dot equals to cy plus du be the companion form of our system. Now the question is, find C and D. You have to find the what's it, C and D for companion matrices for this system, and also find that transformation, find T such that TB equals to D and TAT inverse equals to this C. So we have to find the companion form, and we also have to find the transformation which leads us to that companion form. Okay, since it is given that this system of Y is the canonical form of the original system, so we need to find out first the characteristic equation for this matrix A, and the canonical form for this B matrix we already know it comes as, so D we can write directly, it comes as 0 1, and C can be we can find using the characteristic equation of A. So let's solve for the characteristic equation, which is nothing but determinant of A minus lambda I equals to 0. Alright, so it is it is so it is 1 minus lambda 1 1 and minus lambda, and its determinant should be 0. And it is minus lambda 1 minus lambda 0. It gives us lambda square minus lambda minus 1 equals to 0. Okay, and this coefficient is, so this is our, if you can recall, the last coefficient minus comes as the first entry. So the last coefficient negative we have to take. This is C, it is 1, and this its coefficient is minus 1, its negative is 1, and then 0 and 1. Okay, so this is the canonical form, and D we have already calculated, it is 0 1. Now how can we calculate T? So for T we already know that T should satisfy these two conditions. So the transformation that will lead us to this canonical form should be such that T into B is equal to D, and TAT inverse should be equal to C. Alright, so these two conditions need to be satisfied by T. Now, so T can be anything, so let's assume that it is some, so it must be 2 cross 2 matrix obviously, and let's suppose that its entry is, or let's say that T is some alpha and alpha times of A, where alpha equals to alpha 1 alpha 2. Alright, so this gives us T as alpha 1 alpha 2, and alpha of A will give us alpha 1 plus alpha 2 into alpha 1. Okay, now in order to find out alpha 1 and alpha 2, we can use the conditions. So T into B should be equal to D. That means alpha 1 alpha 2, alpha 1 plus alpha 2 into B, which is 1 0, should be equal to 0 1, and this will give us alpha 1 and alpha 1 plus alpha 2 equal to 0 1. That means alpha 1 is 0 and alpha 2 is 1. Now since we have alphas, we can write T as 0 1, 0 plus 1, which is 1, and then 0. So this is our transformation matrix T. This was our question number 3. Let's move to question number 4. Okay. Suppose it is given that we have the matrix A, which is 1 2 and 2 1, and we have the matrix P, which is given as 1 2. Then find P such that PAP inverse equals to C, that is the companion form, and T into B, P into B equals to T. So since we are talking about companion form, so T is nothing but 0 1. So we have to find that matrix P that would transform the original system to its companion form. The same as the previous question, we know how to find that transformation matrix P. Okay. Again, we will assume that matrix P is of the form alpha and alpha A, and alpha is alpha 1, alpha 2. Then P would look like alpha 1, alpha 2, and alpha into A will give us alpha 1 plus 2 alpha 2 and 2 alpha 1 plus alpha 2. So let's assume the transformation matrix P looks like is having this entry. Now the objective is to calculate this alpha 1 and alpha 2. And we already know that this satisfies PB as D. So let's write it down. Alpha 1, alpha 2, alpha 1, 2 alpha 2, 2 alpha 1 plus alpha 2, and it multiplied with the B given as 1, 2. It should give us the companion form 0, 1. So this will give us alpha 1 plus 2 alpha 2 as 0, and the second one will give us alpha 1 plus 2 alpha 2 plus 4 alpha 1 plus 2 alpha 2 equals to 1. That means 5 alpha 1 plus 4 alpha 2 equals to 1. Now we have to solve these two algebraic equations to find out the values of alpha 1 and alpha 2. So let's do that. So let's multiply this equation by 5. So it will give us 5 alpha 1 plus 10 alpha 2 equals to 0. And let's call it 1 and 2 and subtract this. If we subtract, it will give us 6 alpha 2 equals to minus 1. So alpha 2 will be minus 1 by 6. And alpha 1 will be equal to minus 2 alpha 2, that is 1 by 3. So the transformation matrix P, which was alpha 1, alpha 2, alpha 1 plus 2 alpha 2, and then should be equal to 1 by 3 minus 1 by 6, 1 by 3 minus 1 by 3, 2 by 3 minus 1 by 6, which is equal to 0, 5 by 6. Oh, sorry. It is 3, 2. 3 by 6, 1 by 2 it will be. So it is 1 by 2. Let's move on to another problem. Let's move on to another problem. So we are given the system x1 dot as 2x2 and x2 dot as x2 plus k x1, and this system will be asymptotically stable if k is, we have to find the condition on A. Now since this question is based on designing, so before that let's see, because I forgot to revise that state feedback controller design. So let's first recall about what is the state feedback controller. Okay, so let's start with a linear time invariant system. X dot equals to x plus bu. We can take any y as c x. Now it is given that this system is controllable. It is given that this system is controllable, and the objective is to design controller U, which is a state feedback controller. So state feedback means we only take the information of state X multiplied with a gain matrix K such that this system is anything stable, or we can design for asymptotically stable, whatever be the objective. Now we have already constructed the type of the controller, which is going to be Q equals to some gain matrix K and the state matrix X. Then now if we put it here, we get the system which is written as, by putting U equals to Kx, it is B into K into X. That means A plus BKX. With state feedback controller Kx, the state matrix is transformed as A plus Bk. Now we already know that based on the eigenvalues of the state matrix, we can conclude about the stability of the system. Now suppose the state matrix has all the eigenvalues on the negative half, strictly on the negative half, then what we can conclude, that the system is going to be asymptotically stable. So if all the eigenvalues of matrix A plus Bk are negative or lie on the left half plane, then the system will be asymptotically stable. Okay, so this we already know. So based on this concept, we design the gain matrix K such that the closed loop system is asymptotically stable. So how does the structure look like? So we have system x dot equals to ax plus bu, and suppose we are able to generate all the states K, then based on that we have to design the controller Kx such that when it is fed to the system, it stabilizes all the states x to be to the origin, or the closed loop system is, so this is the closed loop system, the closed loop system is asymptotically stable. Okay, so now with this, let's solve this question. So it is given that uh, we have to find the condition on case such that this closed loop system, or this system, because there is no control, we have to just talk about the system. Let's write it here. The system which is given to us is x1 dot is 2x2 and x2 dot is x2 plus k x1. Now for system to be asymptotically stable, all the eigenvalues of the state matrix A should be on the left half plane strictly. Then the matrix A for this system is 0, 2 and k 1. Now if we see the eigenvalues for this matrix A, we need to calculate A minus lambda I, which is minus lambda 2 k and 1 minus lambda. So its determinant of above gives us 1 minus lambda and minus 2k. That means it is lambda square and minus lambda minus 2k equals to 0. Now for this system, the eigenvalues lambda is given as minus b plus minus b square minus 4ac divided by 2. Okay. Now for roots to be strictly negative, we need that to be real and strictly negative, we need that this coefficient should be negative. Then only whatever is coming from here can also make the system to be the eigenvalues to be strictly negative. But since this, what I'm saying, this is already positive, so whatever is coming from this part will have no role in not which can make these eigenvalues to be negative. So what we can conclude, that there doesn't exist any k such that the system is asymptotically stable. So what we have concluded, that for the given system there doesn't exist any k such that this system can be stabilized to the origin. Okay. So this was question number 5. Question number 6. Now similarly, let's check similar concept for the scalar system. So given a scalar system x dot equals to minus 2x plus k plus 2 into u. So now we have a scalar system but with control u, and here also we have to find k such that the system is asymptotically stable. Okay, since the given system has control U, so let's take up the simplest form of U and then finding out condition on K such that the closed loop system will be asymptotically stable. So the simplest form of control we can take in order to make the system asymptotically stable is just the state feedback controller X. So after fixing the controller, we can write the system as minus 2x k plus 2 into x, which can be written as minus 2 plus k plus 2 into x, that is nothing but k into x. Alright. So now for system to be asymptotically stable, what should be k? We know that for system to be asymptotically stable, the solution for this system is given as e to the power k t minus t naught x t naught, because this is a linear system, linear autonomous system. And for this system to be asymptotically, so when will this solution xt will converge to 0? Only when this k is negative, then only this will be a decaying function and xt will converge to 0, or we can say that the system is asymptotically stable. So the condition for this to be asymptotically stable is any k which is less than 0. What if we have k equals to 0? If we have k equals to 0, then we have its eigenvalue, or this will be converted as xt naught. So it will start at the initial condition and it will remain at the initial condition for all time. So when k equals to 0, the system will be just stable, but when this k is less than 0, the system will be asymptotically stable. Okay, now since we have uh, built up the concept already, now let's try to formulate a controller for a second order plant. Suppose we are given the system x dot, a linear time invariant system is given to us with the matrix A as 1, 4, 0 and minus 1, and the B matrix is given to us as 1, 1. Design a state feedback controller for this system and you have to design in such a way that the eigenvalues of the closed loop system lie on or not lie. The eigenvalues of the closed loop system are minus 1 and minus 2. So we are given a linear time invariant system, and for this system we have to design a state feedback controller such that the eigenvalues of the closed loop system are minus 1 and minus 2. So means the system, we have to design a controller such that the eigenvalues are strictly negative. That means we want to have asymptotic stability of the closed loop system. So for this we have to design the state feedback controller. let's solve this problem. Since we need to design a state feedback controller, let's consider the controller U as Kx, the simplest state feedback control. Now, since it is a second order plant and we are using full state information, so X matrix is x1, x2. So K will have two components obviously. So this is how our controller is going to look like. So the controller is basically K1 x1 plus K2 x2. Okay. Given this controller, we need to find these scalars K1 and K2. We need to find out these scalars K1 and K2 such that the closed loop system has eigenvalues of -1 and -2. Let's solve this. If we write the system with the controller U equals to X, it gives us BKX. So the closed loop state matrix is A plus BK. So the closed loop system should have eigenvalues, means this matrix A plus BK matrix should have eigenvalues of -1 and -2. Okay, so first for that let's calculate this matrix. So A is given to us as 1 4 0 -1. We are calculating A plus BK, and plus B is given to us as 1 1 and K is K1 K2. This equals to 1 4 0 -1 plus K1 K2 K1 K2. So it is 1 plus K1, 4 plus K2, K1 and -1 plus K2. And what will be the eigenvalues of this matrix? Now let's calculate the eigenvalues of this lambda minus, or you can say A plus BK minus lambda I. We need to calculate. So it will be 1 plus K1 minus lambda, 4 plus K2, K1 minus 1 plus K2 minus lambda. This determinant goes to 0. So this would give us let's do all the calculations. It is this minus K1 4 plus K2 goes to 0. So it will be lambda square minus lambda of -1 plus K2 1 plus K1 1 plus K1 plus K2 plus K1 4 plus K2. This is lambda square and equals lambda minus k1 minus k2, and this equals k2 minus 5 k1 minus 1 equals to 0. So this is the characteristic equation for the closed loop matrix A plus BK. Now for and what is the design criteria? This should be designed such that K1 and K2 should be designed such that A plus BK has eigenvalues -1 and -2. So if -1 and -2 were eigenvalues of A plus BK, then what will be the characteristic equation? Should have this eigenvalues, which is lambda plus 1 and lambda plus 2 should be equal to 0. That means it should satisfy lambda square plus 3 lambda plus 2 . So it's a correction in the question. It is -2 and -3, let's say, right? So it is -2 plus -3 plus 2 and plus 3. So this will be 5 lambda plus 6 equals to 0. Now this should equal to this, because this is A plus BK characteristic equation and this is the desired characteristic equation of the closed loop system. So that means this coefficient which is minus k1 plus minus k2 should be equal to 5, and at the same time k2 minus 5 k1 minus 1 should be equal to 6. Alright, that means we have to solve these two algebraic equations. So when we solve it, so we can just add these two equations, and adding will give us minus 6 k1 equals to 2, because it is 7 minus 7 and 12, sorry. So k1 equals to -2 and k2 equals to -3. Okay, so this is the state feedback controller, and our controller will be u equals to k1 x1, that is -2 x1 and -3 x2. So when we provide this controller to this system, the system will be asymptotically stable, and the eigenvalues of the closed loop system will be -2 and -3. Okay, now let's take up the final question, the last question for this session. Okay, which is question number 8. Let's see. So consider the system in the Jordan form which is given as 0 1 0 0 0 0 1 0 0 0 0 0 and 0 0 0 minus 2. Okay, and the B matrix in the Jordan form, it is 10 9 0 1 U, and Y is given as 1 0 0 2 X. Now the question is, check whether the system is controllable. We have to check the controllability and observability. So given the system in the Jordan form, we have to find out whether the system is controllable or not, observable or not. Okay, since we already know that if the Jordan form is controllable or observable, the actual system will be controllable and observable. Now, how to check for controllability by looking at the Jordan form? Since we already know that the diagonal entries of the Jordan form gives us the values of the eigenvalues, and the super diagonal entries gives us the information about its uh, about the geometric multiplicity of that particular eigenvalue, or it tells us uh, allow us to distinguish between the Jordan blocks, and the entry of the matrix B or the matrix C corresponding to the Jordan blocks allows us to conclude whether the system is controllable or observable. Now for this system, let's first identify the eigenvalues and the Jordan blocks. So for this system, the Jordan blocks, the eigenvalues can be quickly defined by seeing at the diagonal entries. So we have two eigenvalues, lambda 1 equals to 0 and lambda 2 equals to -2, and it can be seen that this has multiplicity of 3. Okay, so it has multiplicity of 3 because 0 occurs 3 times in the diagonal, so it has multiplicity of 3, and it has -2 has multiplicity of 1. And so the Jordan blocks, so for -2 we have the one Jordan block only, and for 0 we can see that the entry above this 0 is 1, so it is in the Jordan block, and the entry above this 0 is also 1, so it is in the Jordan block. So this constitutes the another Jordan block. Alright, so we have two Jordan blocks for the system. Now the theory says that if we have one Jordan block corresponding to the eigenvalue, then for the system to be controllable, the last entry corresponding to each Jordan block should be non-zero. The last entry of the control matrix corresponding to each Jordan block should be non-zero. Okay, so now we have two Jordan blocks. So the first Jordan block is this, and the another Jordan block is this. Now the first Jordan block last entry is this one. Alright, and corresponding to this, the last entry of the matrix B is 0. So what we can conclude, and since the second Jordan block is only -2 and the entry of B corresponding to this Jordan block is 1, which is non-zero. So one Jordan block has entry non-zero, but the another Jordan block has entry 0. We are only interested in the last entry of the B matrix corresponding to each Jordan block. So the last entry of matrix B corresponding to the first Jordan block is 0. That means the system is uncontrollable. The system is uncontrollable. Why it is uncontrollable? Because the last entry or the last element of matrix B corresponding to first Jordan block is 0. If it were non-zero, then the system would be controllable. Now can we check on the observability? So now similarly, for controllability we have to check for the last entry of the matrix B for each Jordan block. If it were non-zero, then the system is controllable. Similarly, to check observability, we have to check the first entry of the C matrix corresponding to each Jordan block. Alright, now, so this is corresponding to the first Jordan block and this is corresponding to the second Jordan block. So for the second Jordan block, we have only one entry and it is non-zero. So this eigenspace is controllable. Now for the first Jordan block, we have to check the first entry and it is non-zero. It is equal to 1. So that means that since both the first entries of C matrix corresponding to each Jordan block is non-zero, that means the system is observable. The system is observable because the first element or entry of C matrix, obviously when I am saying the B and C matrix, I am saying the B and C matrix of the Jordan form, not the actual matrix, of C matrix corresponding to each Jordan block is non-zero. So we conclude that the system is observable. Okay, so that's the beauty of the Jordan form, because by converting the system to Jordan block, we can easily conclude about the controllability and observability of the system without even calculating the controllability or observability matrix. We have to just identify the Jordan blocks and search for the last entry or the first entry of the B or C matrix, and then we can conclude about the controllability and observability of the system. So that's all for today. We will meet next week for more interesting problems and concepts. So thank you.